To this first winter school sponsored by the Safari project that I'm coordinating. My name is Alessandro De Luca, and by the Natural Machine Motion Initiative. This morning I should be here with Professor Antonio Bicchi, who apologizes because he had a last-minute call and is right now in Genova. So he will join the school later on. Why are we here? Actually to follow this Natural Machine Motion Initiative. This is a logo of this initiative, which is an open source, in a generalized sense, initiative, and we will talk about this, and you will hear more from this. I would say that this is the right occasion to get involved in this, both by refreshing, I don't know, most of your background is you're PhD students or a young researcher, so you have been hearing about this stuff before, but so we will refresh some theoretical aspect in modeling, motivation, application, and control. And then the important part of this school is the hands-on activities. So I hope you will like the program that has been set up. Don't forget that you have to carry this, so some logistic, carry this badge with the logo in order to have special prizes at the Mensa for the lunch break, if you wish. You're not obliged to be here, but it's very good and relatively cheap. Okay, so we will be together for 5 days, except the Sunday that you can spend in Rome. I think you will enjoy also the nice weather. The last day, there will be a special part in the afternoon, after the competition in the morning. You will have a break, and then in the afternoon we have a closing workshop at my department, which is 100 meters from here. You will find it right there. So this winter school has been coordinated by Antonio and partly by myself. Antonio was supposed to make the introductory lecture. He sent me his slides, so I'm speaking in place of him and adding some motivation from my side. But this school had not been taken place without the real organizer and those responsible for the hands-on activities. And here I list all of them, but maybe you can raise your hand so that people will know you. So Fabio Bonomo, is he here? Yes, okay. Manuel Catalano. Manolo Garabini is preparing his presentation, but he will be soon arriving. Giorgio Grioli. Thank you. Lorenzo Malagia. And Riccardo Persichini. Okay. So they will follow you in the afternoon session. You will be organized in group, but I leave this detail to them. So as I said, Safari project is sponsoring this activity. This is why you have access for free. I know that you may know that more than 50% of applications have been rejected because we wanted to keep the number limited. But as you can see, at the last minute, we decided also to have a registration of the lecture, and this will go online on the NMMI website and Safari right after the school. Of course, you will have an additional benefit of having the hands-on activity here. Okay, so motivation. Why are we here? Why this soft robotic business is taking the flight, in a sense? So robot and humans, there are several activities. Now we have heard that robots have gone out of the factory floor, entering in houses, entering the civil life. So there are several activities where we can need robots, a different kind of robots actually, that cooperate or collaborate with us. interacting, so at the social and verbal or gesture level, and sometimes also exchanging forces, like in cooperative manipulation task. And here you see a picture taken from the NASA JPL with the humanoid torso of NASA, but also in domestic application, starting from the Roomba vacuum cleaner, but in other activities that may require some interaction, physical or cognitive. Of course, entertainment, physical assistance, rehabilitation, and you see here a device, a treadmill, which can be interpreted again as a haptic robot device, because you interact with some mechanical device through your feet and not through your hands. And finally, this Sarcos humanoid used for entertainment, but in fact, it's very important also to understand what kind of interaction between the human and the robot should there be. So robots are everywhere, are coming. There are some special things that we want to focus on. First is more traditional, is teleoperation. So there's a master-slave situation. You have a remote robot or manipulator anywhere. You interact physically with the master, and you receive force feedback from the slave. And this interaction is very important. And of course, the human issues of this interaction are also very important, like fatigue or capability of working for a long time with these devices on. Of course, this brings you somewhere else for doing tasks, but there's a large effort also for being helped here or wherever you are. So what is called human augmentation, you see the Berkeley EX exoskeleton, very lightweight and handy, used mostly for military application, unfortunately, but this is another story, which amplifies your capability. For instance, a soldier can carry this heavy load of 15 kilograms for almost the whole day, not being so crashed, like if it had not this exoskeleton. There are other situations, very interesting, where you have mixed interaction with the environment. So you have physical devices that you touch or that you carry on your body, and you're doing some work in the real world and in a virtual world. So this is another very interesting development. So again, all this situation involves some form of contact between robotic devices and human. So the main issues, or the principal issues, were at the beginning safety. What happens if the robot is not recognizing your intention or applying too much force on your body? And we should always preserve the concept of Asimov, the first law of Asimov. So the robot should never harm you, and so on and so on. So this is motivated researcher in the last decade, I would say, to investigate different type of robots, more lightweight, more compliant, but still with the capability of doing useful and accurate work on the environment. So these 4 videos, gently provided by Antonio, present some human capabilities. Human capabilities that we would like eventually to reproduce. You know that now humanoid robots have gained the media, so they are everywhere because they look like humans, even in face, maybe too much. Maybe we are getting in the deep uncanny valley of these humanoid robots. But here, the point is a different one. So with our muscles, with our actuators, we are capable really of releasing energy in very different way and in the appropriate way. You can see, for instance, in the first video on top left, the highest jump starting at still. Okay, so this requires accumulation of energy and release, impulsive release of forces and energy, so that you can jump 1.60 meters high, standing still. This is a very complicated motion task because it requires both energy and force, but also the timing a correct release of, timing release of these forces. And I would say also accurate motion, because you can jump and then fall out of the stand and you didn't reach any success. And the other way of releasing or using optimally energy, which have nothing to do with safety except for the deepest dive, which I've never done anyway. But in fact, they are related to performance. So Usain Bolt, again, is kind of an impulsive, although it takes almost 10 seconds to run 100 meters, but it's really anaerobic activity for the human, while the marathon runners had to distribute this energy over time. They have to have a reliable way of using their energy in a so-called robust way, if we want to use a control theory concept, so that they don't fail before reaching the target. So all these things, we would like to have it also in robots. Okay, so interaction, physical interaction, and safety, optimal use of energy, impulsive or in the long run. So how would robots look in 10 years from now? Here you see a video recorded at ADAC in Germany, so the Safety Institute for Automobile, where they use dummies for crashing tests. And now, instead of having a car, this is work done mostly by Sami Adadin. So they are investigating the harm, the injuries that can happen when a robot is hitting you. And it can hit you in different places. But the purpose of this video is not showing what this experiment, but looking at the robot. Looking at the robot, the dummy may represent ourselves, very flexible, very harmful, and the robot is very stiff, heavy, and could be fast, and could really hurt the human. So will robots continue to be like this in the next decade or so, or will more and more inherit some bio-inspired morphology, in particular actuation capabilities of the human, which at the same time are able to perform such different tasks, which involves accuracy when it needed, or compliance where it needed, to accommodate for uncertain environment, uncertain forces applied to your body, and still provide sufficient accuracy. So performance is not lost at all. Of course, this is a trivial answer, because the answer question, because the answer is clearly we would like to behave like us. So let's look back at the recent or less recent past. I remember very well all these devices. You may have not seen them at all. I've seen them working. So many years ago, yesterday, there was the famous Unimation Puma robot. This was the first anthropomorphic 6 degrees of freedom all-revolute joint robot, controlled with microprocessors. Okay, actually, the control unit was a PDP-11, a mini computer, which was as big as this. You can tell the size of this. And inside, it had a Motorola 68K CPU with 8 megahertz of sampling and the capability of doing 160 kiloflops operation per second. Okay, so this was yesterday. In terms of machine intelligence, you could do several things. You could do direct and inverse kinematic, even inverse dynamics for the Puma. This is a result of the 80s, I would say. Now, if you compare the computational power with, for instance, today's smartphone, please turn them off if you have it. Well, there's a factor of thousands of improvement, okay? And in fact, in such teeny devices, we can embed a lot of intelligence. So we would think that this is an advance, and in fact it is also for robots and robotic systems. What about motion? Remember that a robot is the intelligent connection between perception, so sensor, sensing, and action. So the motion is always there. Otherwise, you have just a computer. Okay? So progress in computers and miniaturization and computing power. What about motion capability of robots? So yesterday, the Unimation Puma had servo motors. Here you can see one. There have been a lot of advances in this type of devices in terms of power density, size, cost, and so on. What happens now, or let's say 5 years ago now? Still servo motors. Okay, so not really this 1,000 factor of improvement that we had in other devices. So the problem that here we want also to help to address is how to make robots that are soft, so that have a morphology of a human body. They are likely not to hurt if they hit a human being, but still strong to sustain loads, carry things like the industrial robots with 160 kilograms of payload or more. On the other hand, we would like to have it simple, because complexity is not something that we're going to sell in the next year, okay? Or at least the complexity should be hidden behind a very simple interface, okay? So simple in mechanics and in operation, but still dexterous, capable of doing tasks like those that we have seen in the videos, playing soccer. 2050, the robot team is supposed to beat, let's say, the Rome team of soccer. This is likely to happen. Intelligent, of course, we can embed a lot of intelligence, but yet practical in the sense that, as I said, the human command should be easily provided and then realized in an intelligible way, what we call a legible motion planning and execution by the robot, legible for the human. What are the good news? Are we going toward this direction? Well, this slide title, as I correctly understood, I asked Antonio, but in fact I was right, bears the name of a famous song by Bob Dylan. I don't know if you know. Times are changing. Well, also labs are changing. This is the example of the University of Pisa lab, which is fully represented by your part of your speakers and definitely tutored for the hands-on activities. So these are some variable stiffness devices that have been developed over the years in Pisa. I can recognize the VS1, VS2, open, other devices with nonlinear springs acting in agonistic, antagonistic way. But this is a gray area. It's gray, it's on purpose black and white pictures. Why? Because the latest activities in that lab in particular are full of colors. Full of colors means also full of novel prototypes that can be developed very easily thanks to innovative technology in rapid prototyping, thanks to open source software and open source tools, using the web to grab whatever other researchers have already developed and things like that. Okay, so the robotics lab are becoming colored, which means that we can explore new ways and test them in relatively short time. This is a very important thing. And you can see here on the right some variable stiffness actuation, the hands, the Pisa IIT end, and also a modular structure built with the QB modules that you will put the hands on in this school. So what are the enabling technologies for doing this step? So first of all, additive manufacturing. There are a lot of method, technique for building in very short time and cheaply from 3D designs, CAD design, objects that you can use and test your ideas for developing actuation and say, connection devices. Here is a list of several of them. You know that the 3D laser printer are really taking the speed, and the technology is changing. If you have one of these devices bought 3 years ago, it's already outdated. Okay, because there are much more cheap, compact, and performant devices right now. And this is just a list of technologies. Together with this, other enabling aspect that allows to develop new, in particular, actuation devices and full body robots is the availability of open source embedded system, control system, like the Arduino project. I don't know how many of you are familiar, certainly the Italian attendees, but not only. There are new sensors, remember, but because we try to understand internally what's happening in all the parts of our devices, because this allows us to control them in a better way. There are other tools which are very useful in this development, which allows easy to obtain hardware in the loop system, so that you have the hardware developed, maybe rapid prototyped. You don't want to develop the controller in hardware or whatever you need. You have some simulation software that runs, and before doing the last step, you can put the hardware in the loop, just mimicking all the things that you may expect when you're really implementing things. And this is also very useful. And then there are other open source tools which helps to work. So software and middleware, everybody I think is familiar with ROS. Other toolboxes are available in this same sense. The YARP, yet another robotic platform, which is the middleware, very thin middleware supporting the iCube activities, and so on. So these are technologies that may help. But of course, we should join technology with science. What are the main ideas that could inspire us, and actually have inspired many researchers already? They are coming from the biological world, in particular actuators. So we are immediately thinking of how human muscle behave. And the first observation, very simple, you can try it on your body, is that each joint has at least a pair of muscles moving it. And they actually move in an agonistic-antagonistic way most of the time. Actually, this is a modelization, is a simplification of the real actuation in human bones and joints. But you can think of groups of muscles acting in this competitive way. And this kind of activating of those muscles, which is called also co-contraction, allows you to do the same motion in two different modalities. You can have my arm moving fast or slow, it's not important, but moving in a very soft way so that I can deviate from this trajectory very easily, or I can stiffen my muscles and move it exactly like before, but now when I hit something, I will never leave the path. So this possibility of performing motion, but controlling at the same time also another variable, which we called stiffness, and it's very intuitive, but this is exactly what happened in human muscles. And this was the motivating idea also for reproducing these pairs of actuators inside a single joint actuation device. So a couple of things coming from motor, biomotor studies. You will hear probably more from that in one of the presentation, probably by Etienne Bourdet on Monday, I guess. He will talk about motor control inspired by biological studies. So the first thing is this equilibrium point hypothesis. You can read whatever is written, so I will be very briefly here. But actually there's a threshold for activation of muscles, for each muscles, and of course, pair of muscles. And the idea introduced in this paper in 2010, also better said, proved in this paper in 2010, that was an idea that was around even before, is that if you give an external load to such actuation muscles and you release the control so that you leave the system evolve and find its own natural equilibrium, then there's always a situation which is called the equilibrium point, a combination between muscle length and force that is naturally associated to a given load. So the muscle may not be loaded or loaded with 10 kilograms or whatever, then there is a natural equilibrium associated to this condition, okay, which involves the contraction, so the length of the muscles, and the applied force by the muscles, okay? So this kind of agonist-antagonist scheme is what suggests that even artificial single-joint devices may behave in the same way if properly actuated and controlled. So a couple of formulas. Well, the first one expresses the muscle force, which is a function of a couple of parameters, rho and d. D is the form of the muscles. Rho is the way some kind of muscles are able to generate more or less force. Of course, it depends on the physiology of the muscle itself. And there's another variable, which is the a variable at the exponent of the exponential, which is actually the muscle activation. And here you see a formula. It's a positive quantity. This is the plus outside the square bracket. And you can see that there's, again, some physical quantities and parameters in this expression. L is the muscle length. D is the reflex delay, so T is time, so everything happens after some times. This is kind of, in aged people, this times increases. Lambda is the threshold length, so you have to exceed this, and you see that there's another parameter weighting also the time derivative of the extension or contraction of the muscle, okay? So L dot in time. So if you put this together, you have some expression which relates activation, which is controlled by the nervous system, to applied force by a single muscle. If you have a couple of such muscles, then you would like to find this equilibrium, as we said. So depending on the load, there's a different equilibrium. So the steady state equation is very simple. If you think that the muscle apply a linear force, you want to balance a torque, so you need a distance, a lever arm, so R will be this lever arm, F1 and F2 are the forces applied by the single muscle in this agonistic-antagonistic configuration. So you have this balance equation. And now you can assume that R does not change, which is an approximation, but it's okay. And also that the two muscles have the parameters rho and delta equal. So you can write the force F1 and F2 for both muscles and the activation expression. And you introduce now a variable Q, an angular variable, which is the rotation of the joints that these muscles are controlling. Okay? So this is the setup. And now if you neglect the reflex delay, just for simplicity, and assume that you are at steady state, so Q dot is equal to 0, so the joint is no longer moving, and make the assumption that there is no load, but you can change the load, so it's constant actually. You can find an equilibrium position Q bar, so this is the equilibrium position with no external load. There will be other with external load applied. And you have to solve some equation to find this Q bar. But essentially, the outcome is that you have some command, R, which is just the semi-sum of the threshold length of the muscles. Okay, this is quite an important result, obtained in some simplifying condition, but this drives also the design of some controllers for some variable stiffness actuation device. What about the stiffness? Well, first of all, I hope everybody knows this. How you compute the stiffness? You compute the stiffness as the variation, so differentiating, taking the derivative of some applied torque, which balance the external torque, so it's the same, with respect to the variation of the driving joint. Okay? So you can start from a potential energy. You can take the derivative of this potential energy with respect to the position, and you get the torque. If you take a second derivative, so you take the derivative of this torque, you get the so-called stiffness at some nominal operation condition, so at the equilibrium, Q equal Q bar, and in this case under zero external torque. And here is the expression for the muscle under hand. And you can find a parameter there, a C, in the exponent of the E function, which is the so-called coactivation command. And surprisingly enough, this is this stiffness around the equilibrium depends on the difference divided by 2 of the threshold lengths of the two muscles. So we have two functions, C and R, one which is proportional to the sum and the other which is proportional to the difference of this threshold length. So with this in mind, what was the evolution of actuation mimicking this biological behavior? So we started from rigid actuation, so servo motors with very stiff transmission. You can neglect in the limit any deformation. In some cases, this is not true. For instance, if you're using harmonic drives, which enhance the torque level available on the link side of the transmission, you have some intrinsic flexibility. But this is quite reduced with respect to what you can achieve with really variable stiffness actuators. So this concept of having compliant actuation motivated some researcher to develop what is now widely known as SIA system, so serial elastic actuation, which is nothing else than modeled, at least, as a series of masses, spring, masses, and so on. And probably the springs are also damped. And in the most simple realization, you have a mass, just a spring and a damper, and another mass. The first mass represents the inertia of the motor. The second mass represents the inertia of the link. And this is also called elastic joints. So the terminology of elastic joints and serial elastic actuators is misleading sometimes. They actually are the same thing. So in this case, you don't modify the elasticity of the single springs. They may be linear or non-linear, so this is different stuff. But if you have a possibility of using a second muscle, a second actuators, which may be exactly as big as the first one, and this is the typical parallel or agonist-antagonist configuration, or maybe a smaller motor that just act on the variation of the stiffness, and this is the so-called serial configuration, and there are examples of variable stiffness devices of both categories. So you have what is called a variable stiffness system. So with the two motors, you're capable of doing motion and of varying at the same time online, pay attention, not preloading things and then having the system operating. So on the fly, you can modify the stiffness while moving. And of course, this concept can be generalized to what are called VIA systems, so variable impedance actuators. And since impedance contains stiffness, but also mass and also damping, you can imagine that variable impedance are devices that are capable of varying on the fly all the three parameters. I know no system that is capable of doing this at the same time, but there are variable damping actuators and some variable damping stiffness actuators, and so on and so on. Okay, but they fall all in the same category. So, can these variable stiffness actuators that have been developed in the last few years work as muscles for robots? So the problem from the control point of view is moving from the traditional position control, by this, I mean also trajectory control. It's not just regulating a position, but also following a trajectory in the joint space or in the Cartesian space. For stiff robots, so with rigid links, typically not light-weighted, but why not even light, but rigid links and rigid transmission, or as we used to say, rigid joints. This was the first motion task. Now the lightweight series, there are several. This is the KUKA lightweight, which is just the commercialization of the DLR series of lightweight arms. There are other products on the market, like universal robots and so on. What they promise is that you can do torque control. So you can command not a position and have some local controller impose this position or velocity profile, but you can really command torque, torque at the joint level. Of course, this torque at the joint level is useful for applying forces in some point of the structure, typically at the end effector level, but this is a different story. So you can do torque control. Actually, the controller of the DLR, and in part also that of the KUKA lightweight series, and even including the IVA, allows you to modify some parameter to move smoothly from a pure position control to a pure torque control, and to something in between, which is usually called impedance control. Okay? So still you have only one objective, whatever is the tuning of your controller. Now, if you move to variable stiffness actuation robots, in particular multi-degrees of freedom, and you can see here a torso built by the QB modules or the DLR variable stiffness actuated arm hand system. Now you have a point of controlling two things at the same time, and in particular these two quantities that you want to control, mimicking the idea of the human muscles, could be the reference point and the stiffness. Okay? So this is the task that you can achieve. So just looking at one joint, and this is the development at the University of Pisa over the years, they started with a soft arm where the two actuation of the single joint, and in fact they built a 3 degrees of freedom device, manipulator, but each joint was actuated by a pair of McKibben actuators, so pneumatic actuation. It was compliant, it was kind of jerky, not really accurate, but it was implementing this nice idea. In 2003, they developed the first version of the variable stiffness actuators, and you can see here a top view, and the three, let's see, just to be. So these three locations, so here is, these are the output shaft of the two motors, and here is the link rotating around its output shaft. So for describing this system, you need to know the position of the motor 1, the position of the motor 2, and the position Q of the link. Of course, they interact through nonlinear springs or linear springs connected by nonlinear kinematics. And this was later developed into the VSA-2 in 2008, and then here is a VSA with harmonic drives. This is also a concept used at DLR. And today you will see the VSA cubes, which are small, compact, low cost, and this is the rest of the story. Of course, variable stiffness actuators are worldwide diffuse. Here you see realization at IIT, at DLR, in Korea, Japan, and so on and so on. So this is not just a brand from University of Pisa or the Italian gang. If you look at the diffusion of technical scientific papers on this subject, here you have a story on the left. You see a chronographic distribution of devices, while this plot is a plot obtained with Explore, and IEEE Explore, where you search for keywords which are somehow related to this problem, so active compliance, adjustable damping, compliant control, electric transmission, and stiffness control, and so on and so on. And you see that between 2000, this is 2000, and this is 2010, you have seen a huge increase in activity. So this witnessed the interest worldwide to this topic. So let's say a few words on this, and then I have to skip things. This will be one type of variable stiffness actuation that we will consider, so the agonistic-antagonistic arrangement, so two motor and one link, nonlinear springs connecting the motors to the link with definition of variables. And this is what is in fact embedded in one of these cubes that you will be working on. And here you see the torque characteristic, a very nonlinear expression of the difference between the position of the link Q and the position of each motor, theta M1 or theta M2. So these are the torques acting on the transmission on the two sides. And again, here we can mimic the same analysis done for the muscle, so we can find a natural equilibrium position, for instance, with no external load, putting velocity to 0. And we find that the reference position actually is the average of the motor position. Okay? So in particular, if you have the two motors, one pushing on one side and on the other side, there's no motion of Q, but of course you can, you can implement some position, but also some stiffness. So the equilibrium joint position is proportional to the semi-sum of the two motor position, while for the stiffness you do exactly the same. You take this expression of tau, actually the tau is the sum of the tau m of each motor, and you take the derivative of that with respect to the position of the link at the current equilibrium configuration, and you find a parameter appearing in the exponent of the exponential, which is k, which is the stiffness preset, and this is proportional, or it's the semi-difference of the motor position. So again, you see that this device emulates completely the behavior of the antagonistic-agonistic muscle pair in humans. And in fact, you can set up a comparative table here. So what we call the reciprocal command or reference for the muscles, R is the Q bar in the agonistic-antagonistic variable stiffness actuation. So what we call coactivation command in the muscle is the stiffness preset K in the mechanical device, and then an expression for the definition of the stiffness, and then there are also relationship in this table, but you will hear more on that. Now, the nice thing is that what about characterizing this transmission? These are plots obtained on human muscles, so the elbow flexor and extensors, measured through unloading the arm. This is a result taken from this old paper of '92, and you see this typical profile depending on the load. And these are the profile that you obtain when you characterize the variable stiffness actuation cube. Again, this plot relates the link position to the external load in the condition of a given reference position Q bar, 0, and pre-stiffness value, so the K. You see on the left you have a situation for K equals 0, on the right the situation for K 25, and you see that this, of course, changes the characteristic, but this type of profile is exactly what you find in the human muscle. Okay. Well, I will skip this part because of time. So this concept have been used, and this is really daily bread for Antonio on the hands, and in particular there are many robot hands. Just the concept here. Research in this area, including Antonio's research and of his colleagues, was really looking for anthropomorphic hand, 5 fingers, if not 3. Multiple degrees of freedom, opponent thumb, and so on, with a lot of sensor, a lot of actuators, and some intrinsic compliance due to the fact that this actuator had to be relocated and connected through steel cable and pulleys. So very complex devices. At some point, people realized that maybe this is not the best way of doing things, and in fact, here is the second, not just the technology, but also the enabling science results were coming from the concept of synergic motion. So in particular for the hand, there are some studies that had shown some synergy of motion of the various degrees of freedom, the many degrees of freedom of the human hand, and some constraint that so that the motion of the single elementary joint cannot move differently from what the other are doing. So there is some cooperative motion which can be represented by an elementary combination of motion. This is the concept of synergy. And in fact, here you can see that if you use this concept of postural synergies, which are nothing else than a statistical quantity, the principal component of the grasp covariance matrix, for those of you who knows what this is, but it's some related to how the hand is grasping the object. You can extract this computationally, and then you can recognize a first principal component, and this principal component is able to explain the motion of 50% of the type of the human grasp, which is already a rather surprising results. If you take two of these elementary synergies and you can combine them, you can cover up to 84% of the typical grasp, with 3 up to 90. Now you have to add many more synergies if you want to cover all of them, because the human hand can take and manipulate objects in a multiplicity of ways. We never use them, but they are there. Okay, so the concept of synergy is simplifying things. So each synergy can be actuated by a single motor. Of course, these motors map into all the degrees of freedom of your hands. Okay, so for the hands, it's just a matter of doing similar thing as for the full robot. So we want to make and use hands that are soft yet strong, and again simple and dexterous. Dexterous in here is very clear what we mean, and so on. So what is the idea? Is exactly the same idea of the variable stiffness actuation for robots. So soft robotics technology, this is a terminology that embeds or covers all the things, and some scientific theory behind, which is the theory of human synergy, not just human muscles like in the actuators. And soft synergies means that we have a grasp, but we can also comply with the object that we are grasping. So there will be a deformation with respect to the reference position, which is the one associated to the synergy. And if you implement this, you're able to be very robust to adapt to a multiplicity of objects, and you will see more on that probably in one. And this is the PISA IIT Soft Hand. With just one single motor, you can see it on board and doing multiple grasps. Maybe some of you have seen some video of that. So why this natural machine motion initiative? Okay, so this is the storyline of variable stiffness actuation and variable impedance. We started with single degrees of freedom, then integrating this in a larger structure, multi-degrees of freedom, and then going to application. And there are a huge number of applications for locomotion, for manipulation, as we have seen. If we want to realize high dynamic tasks like throwing as far as possible an object, if we want to have a physical human-robot interaction under safety constraint, which means that we have to comply, detect collision, and react in a very compliant way, if we want to do haptics or telemanipulation, wherever we have an instructor and environment that presumes that you may collide with this environment, and so on and so on. We could go on forever, but the idea of this initiative is that a group of very smart researchers can think about application, but this does not cover the whole world, okay? So we believe, we suspect that there is a much wider set of applications that could be used, and the idea is to do crowdsourcing. So building up a community, distributing materials, sharing ideas, sharing results, experience, so that the trust in this will be larger, and some unexpected application may pop up somewhere in the world. So this is the Natural Machine Motion Initiative, and this is the logo of this initiative. So the main issue were cost to develop these devices, time needed, you need some expertise, so the know-how, and also the fact that if these devices are not diffused in the world, you have problems. No? You have problems because you don't have this kind of gathering of idea, of factory producing solution. So the solution that are suggested is having something which has a lower cost, it's modular, so that you can build your own robots. Everything should be public access and should be easily utilizable. And then there should be an open forum of discussion, like wiki, that, where everybody is putting his experience on. So this means that a fully open platform is needed, both in software and in hardware, the electronic and mechanical part, and this is what the Cube is doing for you, so that you can either buy a full set or design your own following the datasheet given, both for the mechanical part and the electrical part. Okay? The open paradigm follows some previous idea, the Berkeley type of copyright or Creative Commons licensing, which helps in the diffusion. And the idea here is that we want to start creating this community. And there are other examples in the computer science or even robotic world, like the Linux development or the iCub or even the Arduino. The website, I guess that you have already visited it. It's divided in three main sections. One is exploring, one is documentation, and one is joining events like this one. So exploring, you can find several drawings of actuators, accessories, full system, and so on, so that you can make also things by your own. The tools are data sheets, are simulators, for instance in Simulink, and in other sim mechanics, libraries of codes already developed by the group and by the other member of the community. And in fact, you can look also at some initial project like the bimanual grasping and handover, or the Arduino interface for one of these devices, the QB Move Maker. Finally, the documentation, of course, a forum and a frequently asked question, and all the scientific documentation. These are two papers that you find there, and by the way, you will hear exactly their main author, or the first author, Bram van der Borgt and Giorgio Grioli, talking about these results in this school. This is one example of a VSA datasheet. Actually, the project Viactor has developed this kind of result. So how do we qualify one of these actuators? Like a DC motor. DC motor, you look at the characteristic of current torque or whatever, voltage torque, and this is it. Here you have multiple things to keep under eye. It's not just motion, but it's also stiffness, range, speed of variation, and things like that. So you need a data sheet which can be used for any new devices. And this was the effort here. You see some of the parameters that are of interest: maximum speed, peak torque, minimum stiffness, maximum stiffness, and so on and so on. And you can find some of this data sheet in the website. And if not, you will find it in the website of Viactors. Also the drawings, the mechanical interface of the electronic part, these characteristic curves, and things like that. Okay. Finally, through the website, you can reach events like this winter school, and you can contribute by sharing your project, and most important, taking the initiative. Once you are become acquainted with these devices, and if you like it, as we hope, you can become an ambassador of these things. There's no money involved at this stage, remember. And this is the QB Move that you will be working on in the hands-on session. And I can stop here. I can just go very quickly through the program. There are no major changes, just a switch of things, but we have, I think that manual is already in the program that you get distributed this morning. So this is today, and you see that after the first session in the afternoon, after the coffee break, you will have the first 3-hour practice hands-on activity. This is tomorrow morning. You will hear Bram doing a review of BSA and myself again highlighting some control aspect in elastic joint and variable stiffness actuation joints. And then in the afternoon you will have the introduction to the demos and to the competition, and then it's Saturday night. And on Monday, we will have Etienne Bourdet talking about motor control, inspired by these biological studies. And we will have two other presentations on, let's say, optimal control and cyclic control, best use of BSA for cyclic motion. And then again, in the afternoon, 3 hours of practice hand-on. And on Tuesday, this is the switch. Fabrizio Flacco will talk about estimation of stiffness in these devices, while most probably Nikos Tsagarakis, and if not, Antonio Bicchi will replace him, on the design of soft actuators. Again, 2 sessions in the afternoon on practice hands-on, and on Wednesday in the morning, the final demos and the competition. And then you will have free time. But you're kindly invited, actually this is part of the school, to the afternoon workshop, which will take place in my department here. We will start with the presentation of the winning team of the winter school. There will be other attendees, not just the person from the school. There will be the partner in the Safari project, the reviewer from the European community, students from my department, and other Italian researchers coming on purpose for this event. Okay, thank you very much. Coffee break.